Hello everyone. So right now what we're going to do is discuss a seemingly light or simple inverse trigonometry problem. Alright, so what if you are asked, and okay, by the way, remember sine, first of all let's just kind of get some background a little bit, so or refresh our memory. What in the world is just a sine, a trigonometric function sine, right? So sine of an angle theta is equal to, it's equivalent to actually, the opposite over the hypotenuse, opposite side over the hypotenuse of a right triangle having that angle theta here, and then this is being the opposite side, and this being the larger side, the hypotenuse of a right triangle. Or remember the unit circle concept that you have, and this we derive from this triangle idea. If you have a unit circle radius 1, basically, any y value, xy, will be, this is my cosine for x, so cosine theta, and this is my sine theta, if this is the angle theta here. Okay. So, and this is because, again, this is going to be a radius 1, right? So it's going to be x over 1 is cosine theta, and then opposite, which is y over 1, will be, or the hypotenuse would be sine theta. Okay, now, what's the maximum you can even get for sine, right? It's a 1. And then minimum is negative 1, right? Or if you consider the fact that opposite of a hypotenuse cannot be larger than 1, right? Because hypotenuse is the biggest side, and we're dividing, then what we ask a question such as, oh, what is my, and I'm going to talk about this in a moment, what is my inverse function, sine inverse or arc sine, of a number such as, let's make a number, natural number like 5, okay? And what I always do is I lie to my students when I teach them and tell them in trigonometry class, especially when I'm doing inverse trig, I say, look, there's no such thing. There's no solution for this. It does not exist. Look, sine inverse of 5, well, this is not in domain, right, which is negative 1 to 1. The minimum is negative 1, maximum is 1, seemingly so, right, of arc sine of a ratio x, okay? But, look, mathematicians, you tell them, look, this can't happen, this doesn't exist, guess what? They still try to overcome that, right? Go back to when the irrational numbers didn't exist, right? You make up square root of 2, what's the area, what makes the area 2 when you square a side or something like that, right? And it's like, well, there's no such numbers that are rational. Well, you make up an irrational number, square root, the radical sine 2, and then you just keep it that way. What about something squared giving a negative number, right? Doesn't exist. Or do we make a little I for imaginary part, and then we have complex number theory, and that helps us a lot in our life today. We wouldn't be able to do a lot of things without complex numbers. Okay? Complex numbers, ready? So, arc sine of x, instead of saying, oh, this does not exist, or undefined, I'm going to call this a number z. Okay, I'm going to call it some number. Let's see, let's try to get more insight into what the z can be. So now, let's say, let me remember this Euler expression for a complex number. Any complex number is e to the I, let's say theta, is equal to cosine theta, the real part, plus the imaginary part is I times sine theta. Remember we discussed that. And then we also discussed the Morav's theorem using this result as well. But now what I'm going to do is, I'm going to look at that sine theta, right? And if I also try, let's try this. What about e to the negative I theta? What would that be? Let's put that, or I negative theta, right? Let's do a cosine of a negative theta here. Put a negative theta for everything, right? Plus an I sine of a negative theta. And guess what that is? That's an even function cosine, so it's just cosine of a positive theta back, positive theta. And then that's a minus coming out because it's an odd function, so minus sine theta I, okay? And then if I subtract the two equations, let's try that. The cosines will cancel, right? And you have actually that e to the I theta minus e to the negative I theta, okay, is equal to here I sine theta, and then here minus a negative I sine theta. Okay? Let's divide this by 2, divide that by 2, and you have I sine theta is equal to, this can be a minus minus plus, and so you have 2 of those. So divide by 2, you have I sine theta is equal to e to the I theta minus e to the negative I theta. Actually, let me put 2 here. 2i sine theta, right? And then divide by 2i, okay? Or multiply it by 1 over 2i. Let's do negative 1 half I. You'll see that cancels. Negative 1 half I here, negative 1 half I here. And then you actually specifically get that this becomes a 1. So sine theta is equal to, let's do negative e to the I theta minus e to the negative I theta all over 2. Okay. And actually, let's just do make it easier looking. Let's do 1 over 2i. Let's keep it that way. And 1 over 2i, not to cause any confusion with arithmetic. So over 2i, we get a negative sign there. All right. So there's an expression for sine of theta in terms of exponentials, right? And complex and imaginary numbers, right? So now what I can do is I have sine inverse of 5 as z. Well, what does that do for us? First of all, let's take sine of both sides, all right? So sine of z is now, well, that's going to equal to 5, right? Inverse function. So if you take sine of the sine inverse of 5, you get back to 5. At least that's supposedly what would happen. And so sine of z is equal to 5, right? Let's try going back to this motion here. So sine of z is 5, right? And then what is also sine of anything? Sine of theta was this, right? Sine of z is going to be e to the I z minus e to the negative I z. Looks kind of messy, right? All over 2i. And you may think, well, okay, so what? That makes it even more complicated. We can do something with this. Watch. Let's go over here and we may even say, if you like, let maybe y equal to e to the I z, okay? Then we have that 5, let's use 5 here, 5 equals, and then let's multiply by 2i here. So 10, get rid of the 2i at the bottom, 10i is equal to y. And then e to the negative I z will be a 1 over y, right? So minus a 1 over y. This comes right here, okay? And so if I make this into actually a quadratic equation in standard form, having, of course, an imaginary part, so, it's kind of messy. But look, you have y squared, and then minus a 10i y, and then minus a 1. I multiply everything by y also. And that's equal to 0. Okay. I know quadratic formula, right? So remember, quadratic formula, which would be negative b squared plus or minus the square root of negative b plus or minus the square root of b squared minus 4ac, the discriminant. And then what, all over 2a. So let's try that. My y will be negative of the b, so positive 10i, plus or minus the square root of 10i squared, negative 10i squared, doesn't matter. It's a 100 times a negative 1, negative 100. And then minus a 4 times a 1 and a negative 1, so plus 4. Okay? All over, what is it, 2? 2a, 2 times 1. So y is equal to 5i, okay? Plus or minus, now what is the square root of negative 96? 96, right, is 24, right, times 4. So square root of that is actually, what is it? It's 16 times 6, so you can do 4 root 6i, or 2, because we divide by 2 root 6i, okay? That's what we have left when we divide by 2, the square root of 96 negative. You have I coming out and the square root negative, right? And so we have this as a result. And what is that? That's equal to my e to the I z. Well, looks like we have something, right? And actually it's all imaginary. 5 plus or minus 2 root 6 I, right? What do I do now? Well, take a natural logarithm of both sides. And so I have iz, getting back iz, is equal to natural logarithm of these strange imaginary numbers, right? Gives me iz, right? ln of this, the inverse of the exponential. And then guess what else? Divide by I, right? So z is equal to 1 over I, okay? And then what is this ln of this number, and then over times an I? Remember, ln of something times something is ln of the sum. It's the sum of the ln. So natural logarithm of 5 plus or minus 2 root 6. Let's forget the I for a moment, and then plus natural logarithm of I. Okay? All over I. Okay? And that is a monster in itself, because what is natural logarithm of an I, right? And so that's the next step that I would ask you to consider on your own. But let's look at that. I mean, because this is almost there, right? We actually have some imaginary part, some real part maybe, to this solution of what in the world is an inverse arc sine of 5, right? And it looks like that's something there. Let me try. I'm going to finalize this. Let's first look into quickly what is my ln of I. What is that, right? Let's call this W. Then go back and take e to both sides. You get I is equal to e to the W, right? And then what is W and what is I, right? This is an imaginary, this is actually 0 plus I plus 1I, and equals to e to the I negative IW, right? Also, that's another way to write e to the W is I negative I is just positive 1. I'm just trying to think what possibility they can use. So now look, this would be cosine, the real part of a negative IW should be 0, and then sine of negative IW should be equal to a 1, the imaginary part. Okay? So what we can see from here is when is cosine 0 and sine is 1? The IW, actually sine would be, so negative sine of IW would be 1, and so cosine still of IW would be 0. I'm just going to take away negative sign and use the odd and even function identities. And so we actually would have that IW should be that in radians, what? The negative pi over 2, or right, or what we do, 3 pi over 2, but let's do negative pi over 2 plus a 2 pi k. Okay? That's many radians. So you have sine is negative 1, cosine is 0, it's a negative 90 degrees, right? And you can add a bunch of circles to that negative 90 degree angle, negative pi over 2 plus 2 pi k. And if we divide that W by negative I, by an I, you actually multiply by negative I, so W is equal to, let's do pi over 2, and then, so we can say minus, but I'll put minus there, but it really doesn't matter because it's an integer. Like this, and I, okay? I multiplied left and right sides here by negative I, and so you see that W is messy in itself, but this is still feasible. We're doing something, right? Like we're getting some kind of result, because now for ln I can put in, remember that's my W, ln I is that, and what happens is, remember I'm dividing by I, ln I over I, so that I will go away, and so my Z should be something like this. Let's finalize this as, so let's do this, ln I over I will be pi over 2, I'm going to use a plus now, but use a capital K if you like, plus 2 pi capital K, just an integer, negative K basically. That's the real part, okay? Because I'm going to ln I over I, and there's an I there. So we have a real part, okay? We have many real parts. And what about this? What's 1 over I? Think about it, it's a negative I, right? So we actually have a minus I ln of, and you have two things to deal with here. But what's nice is they're both positive here. These are just real numbers. So here's a real, there are two real numbers, 5 plus 2 root 6, a real number, 5 minus 2 root 6. Again, both this is root 25 minus root 24, root 25 plus root 24, okay? And so there we are. This is something. This is my arc sine of 5. And you can check. In fact, the Google calculator is pretty nice. If you plug in, oh, what's my sine of all this? Pick a k, k equals 0. That'd be easiest, right? Do sine of pi over 2 minus I, and then ln of, let's say, 5 minus 2 root 6. Okay? Guess what? You'll get something close. If you're really close, you're going to get something close to, if not exactly, 5. All right? So I just thought something very, very interesting to look into, and I hope you enjoyed the mini lecture. All right? Thank you so much. Have a great day.